it was on June the 10th. Sorry, it wasn't on June the 10th. My apologies. Our last meeting was on May the 13th. New ways of looking at Io's volcanoes, the first big moon of Jupiter. Fascinating talk by Professor Lionel Wilson. He really gave an insight into what we know about Io. I learned a lot. So if you missed that talk, you probably noticed that we're recording this one, and you can get past lectures going way back decades. We've had everybody from the BBC's rock star astronomer, Professor Brian Cox, through Astronomer Royals, etc., etc. There's a big list on the website, astronomy.ie, if you want to check them out and catch up. So that was our last talk. There'd just been, on Monday, May the 13th, the massive aurora on May the 10th, the previous Friday, which we predicted on the day before. And those of you who aren't getting our aurora predictions, do check out our social media, Facebook, Twitter, Instagram. It's on the bottom of our website, the links to each, whichever one you're into. And tonight, actually, after this meeting, we'll actually be predicting the aurora for tonight. We've already warned people yesterday that it's coming. Seems to have just materialized. I took a quick look at some of the spacecraft data before we started. So that should be a bit of fun. Some clear skies forecast too. So it could be like May the 10th. Maybe not as good, but at least people will hopefully see some. Not a great time of the year, as I'll explain later. So that aurora from May the 10th, NASA says is perhaps the biggest in 500 years. And it's the front page of our June magazine. So most of your members get the magazine, but those of you who aren't are very welcome to this talk and can get the magazine. Sign up anytime on astronomy.ie. We're always looking for newcomers, especially beginners, kids and families. So tell all your friends if you are already a member and join up after the meeting if you're not yet a member. If you missed me talking about the aurora, if you go to astronomy.ie/audio, you'll see the interview we did with FM 104, looking back on the aurora a couple of days after it happened. Another thing that happened after our last meeting was that the International Space Station was blazing over. We were hoping for a bit of a space chase as new astronauts joined the astronauts on board, the 7 of them there at the moment. Fortunately, kept getting delayed and we didn't get that space chase, but we'll hope in the future. The next time it's in evening skies is July 7th to 24th. Another thing that was happening last month and is happening again tonight is the Beehive star cluster is next to the moon. So we'll tell you more about that. We even had Saturn near the moon on May the 31st. Some of you may have got up the crack of dawn to see it. I tried, and the clouds just wouldn't get out of the way at the right time. So it's always an exciting time in Astronomy Ireland. As well as the monthly magazine, we have a weekly email that goes out to remind all the members what's happening. There are talks in schools we do all year round. We have the big annual Starbecue Star Party, Ireland's biggest annual star party. August 31st is the date this year, last day of August, easy enough to remember. We'll be able to show you the wonders of the universe through giant telescopes in the really dark sky of the Wicklow Mountains. There are evening classes happening at the end of June. I'll mention those at the end, and for beginners starting in October. So we think the world's most popular astronomy society, loads of things happening, so do join. At least follow us on social media free of charge. You can afford about €1 a week. You can become a member of the world's most popular astronomy club, aimed at beginners, and we'd love to have you. So that brings us nicely to the main business of the evening. We're delighted to have Thomas Moore from Queen's University Belfast, who, as I said, was part of a study looking at a supernova that seems to have revealed what happens when giant black holes or neutron stars are formed as a result of this. He's going to explain everything. He's currently a PhD student in Queen's University. So over to you, Thomas, and thank you very much for giving us the details of the story that we've covered in Astronomy Ireland magazine.
Thank you very much, David, and thank you to all of you at Astronomy Ireland for having me give a talk. I'll just share my slides here. I did check that they worked on the system, but yep, there we go. Can I just get a thumbs up or acknowledgement that the slides are visible to
looking
you?
Great, looking great.
That's fantastic. Yeah, so it's my privilege tonight to talk to you a little bit about supernovae. I wanted to give an overview of supernovae, try and set the scene, and then also discuss some exciting new results. The exciting results, as already been mentioned, are some of my own that we were fortunate enough to publish just at the end of last year. So I'm a PhD student, not quite finished just yet, but getting there at Queen's University Belfast. But also, I've added quite recently a new affiliation to the European Southern Observatory. So I'll speak a little bit about that at the start, just because I think it's quite interesting, and I think it might add something to the talk. So supernovae are astrophysical explosions, and astrophysical explosions can come in all shapes and sizes and types. But supernovae specifically come from the deaths of stars. There are a few ways a supernova explosion might occur, and there are two main pathways that we think form these kinds of explosions, but they do come from stars. They're not the energetic outbursts from the centers of galaxies or other types of explosions or phenomena we see in the sky. They do come from stars. And the name itself, supernova, comes from novae, which are classical novae outbursts from stellar systems, but they're supernovae. They're many times more luminous and come from outside of our own galaxy. Move on to the next slide. Yep. So the reason I want to start talking about the European Southern Observatory is that I'm fortunate enough to be spending some of my PhD based in Chile, which is indeed where I am right now. So it's about 2 p.m. Local time. So I am very glad that this is an online and remote Zoom talk. On the left here, I'm showing the wonderful ESO La Silla Observatory site. It's the oldest observatory of the European Southern Observatory in Chile. And I've marked here in the white arrow, I hope you can see it on your screens, where I'm sitting at the minute. So this morning I made the journey from Santiago, which, if you can see my cursor, or maybe I can just describe where it is the top middle image on your screen, is the offices in Santiago where over 100 astronomers work. So I traveled from there this morning to La Silla, and I'm just very glad that the internet is working well. ESO also has an office in Garching, just outside of Munich, which is the bottom image in the center. And ESO obviously runs and operates the most productive ground-based observatory in the world, which is the Very Large Telescope, which is the collection of 4 8-meter class telescopes. And also, it's fortunate that Ireland are the most recent ESO member state. So Ireland joined in 2018, and I'm sure glad they did. That we did, and of the dozen or so PhD students in the office here in Chile, 2 of us are from Ireland, so we're slowly and steadily taking things over here. The reason I've come to this observatory is to use this telescope. We'll be starting tomorrow night, and we'll have 3 continuous nights of observations, hopefully. And it's part of the PESTO survey program, which started out of Belfast, started by my PhD supervisor. And it's a bit of a mouthful, but it's the Public European Spectroscopic Survey of Transient Objects. And the transient objects, in my case, being supernovae. They're called transients because they appear in the night sky, but also they fade away and they disappear. So they're transient objects in the sky. The telescope is called the New Technology Telescope, which is one of these examples of the funny naming schemes in astronomy, because it's now 40 years old and getting a bit long in the tooth for observations. But it's still a very capable, wonderful telescope to observe with. And with a nearly 4-meter diameter mirror, it's still very capable in today's landscape of 8 to 10 meter facilities, or indeed the James Webb Space Telescope. I've included an image here just from a run here at the observatory I did before, and my close collaborator and friend Shubham where we were here observing in 2022. But I just think to really appreciate the scale of these telescopes, you always need to have a human standing in front of them to really appreciate just how uh, big these things are, and how amazing it is that we get to use these facilities to study the universe. This talk's on supernovae, and I always like to start off any talk on supernovae just admiring the sheer beauty of these objects, and just in being amazed at the ancient and historical astronomers who recorded when these supernovae happened. These are nearby remnants of historical supernovae, so they are within our own galaxy for the most part, although 1987A is in the Large Magellanic Cloud. And here I've included the dates from when the supernova happened. They're beautiful, but they're also diverse, and that's something I will come back to later in the talk, is that not all supernovae are the same, and indeed some of them show remarkably different features. Some of them look spherical, some of them look more elongated. And supernova 1054, the William Parsons, who built the Leviathan telescope at Bear Castle, famously thought it looked like a crab. So that's an interesting story, but I certainly don't think it looks particularly crab-like. And then there's the beautiful supernova 1987A, shows these remarkable rings of material that the supernova ejecta has been moving through in the decades since that explosion. And supernovae are quite common in astronomical terms. There's one per galaxy every 50 years. So in the observable universe, there's supernovae going off every second or so, and we're lucky to be able to observe between 10 to 12 new supernovae every single day. So there's a phenomenal number of these supernovae happening in external galaxies that we're able to study with telescopes like the New Technology Telescope. But what are they? This is an important question, and really the core of my PhD research, and the core question of the field that we work in. So here I've taken a plot of a simple supernova family tree, and there are two main progenitor systems for something called a supernova explosion. One is a white dwarf. A white dwarf is a stellar remnant. It's the future state of a sun-like star. As the star evolves, it sheds its outer layers and leaves behind a white dwarf star of mostly carbon and oxygen. And this exposed stellar core will just radiate away its energy over the lifetime of the universe. But something makes it explode. And I'll get back to this mechanism later on and discuss it slightly, but something causes this white dwarf to exceed a mass, which is 1.4 solar masses, known as the Chandrasekhar mass, where it can no longer support itself against gravity and collapse. And that forms the white dwarf explosion, which is a thermonuclear supernova, which is the famous type 1A, which is used for cosmology and is used to study the expansion of the universe. It's a fantastic and tool for astronomy, and that one supernova in particular is kind of standard, and you can use it as a standardizable candle to measure distances, because the supernova explosion happens when the star reaches this Chandrasekhar mass of 1.4 solar masses. So the initial conditions of the explosion are assumed to be, if not exactly the same, relatively similar, such that we can infer something about the universe from observing type 1A supernovae. The other type of supernovae I think are more exciting. I'm slightly biased because that's the field that I work in, are the core collapse of massive stars, which show hydrogen and helium lines in their spectrum, and they have this myriad of types of type 2, type 2b, 1b, 1c, based on features we observe with telescopes like the NTT in their spectrum. Oh, the lights just flickered here. So how do we know there's hydrogen or helium in these explosions? Well, to do that type of measurement, we use a spectrograph, and here's a rough graphic showing what the spectrograph does. So here, for any given target star, light from that star is hitting Earth. It's coming as light from the sky. Essentially, what the telescope does is it places a slit over that star and then projects that light through a grating, which splits the light like a prism, and that's mapped to a detector where we see the spectrum formed. So we take the light from a single source and we spread it out, and we look for characteristic lines of elements or ionized species of those elements that we might recognize, and we can learn something about the atmosphere and environment of the exploding star. And like I said, we're searching for specifically the signatures of hydrogen or helium or things that we can use to classify and learn about the supernova. Here's another graphical, also a little graphic showing the two flavors of the supernova progenitor systems. On the left is this white dwarf explosion. Here, the smaller white dwarf is accreting matter. It's gathering mass from a companion star. Once it reaches that 1.4 solar masses, it explodes. In the second scenario, where the core collapse occurs, the star is trying to support itself against gravitational collapse by fusing hydrogen into helium in its core. Eventually, this fuel is expended, and the star collapses against gravity. It collapses under the force of gravity, and rebounds out as an explosion, the core collapse of a massive star. So just to hammer this point home, because I think it's something amazing that we know about these stars, is how they evolve and how they end their lives. Because although astronomy although modern astronomy is relatively recent, by observing lots of stars at different phases of their evolution, astronomers have been able to piece together the life cycle of average and massive stars, such that we can start inferring what the star that went supernova must have been like. So following this top track, average star, sun-like star, it evolves through a red giant phase, it puffs up, blows off all this material, forming a planetary nebula. It's beautiful nebula, the like of which some of you might observe in the night sky, leaving behind this white dwarf remnant. And then something happens, and there's a supernova explosion. Following the bottom track now, there could be a massive star, forms a red supergiant that undergoes core collapse, forming a neutron star or black hole from the ensuing supernova explosion. So yeah, type 1a supernovae come from these binaries. They're exciting, and they've been used as tools all across astronomy. But the actual mechanism by which they explode is still an open research question. The exact trigger is not known, and this is a modern and cutting edge area of astrophysics research. People are trying to figure out exactly why this happens, and of course there are hypotheses for this. One is the accretion scenario on the right of this figure, where the white dwarf gathers mass from the companion. The other scenario is on the left of this plot, is two white dwarf stars merging. They orbit each other, and over time their orbits degrade until they eventually merge, forming this explosion, or some sort of explosion at the surface of the star might trigger the explosion of the core. These are still things that are being thought about and researched, and James Webb Space Telescope is being used to study some of these scenarios in detail by using the extra wavelength range that James Webb gives astronomers to investigate. Type 1b and 1c and type 2 supernovae these require an iron core to collapse and explode. And we know that a stellar mass at birth above 8 solar masses is sufficient to form an iron core that can collapse in such a way. Core collapse explosions is a different mechanism to type 1a supernovae. And because it's not a explosion at a specific mass, there's no tipping point above which you undergo a thermonuclear explosion like a type 1a. This is the collapse of a core, and the core could have any mass above a certain range. This produces quite a diverse range of outcomes, and there's a diverse range of progenitor stars that might have formed that might form these explosions. Here's a graphic just trying to explain what I've been trying to say here in words, is that the gravity is pushing down on the star, trying to collapse it, but the heat that's generated from the core has this outward pressure that is sufficient over the lifetime of the star to keep the star inflated and avoid collapse. But eventually that fuel runs out and gravity wins. And it could form something like a type 2 supernova, which has this hydrogen in its spectrum. And type 2 supernovae are fascinating. And quite remarkably, we have seen the star that has gone on to form a type 2 supernova before the star has exploded. Here on the right, I have an image on the left. So if we just go row by row, there's an image on the left, and then those crosshairs, there's a little red point. And then on the right is the supernova that came from that star. So we can actually see the star that exploded in archival observations of these patches of sky, which I think is amazing. To be able to look back and figure out what stars exploded, that's a real incredible thing for astronomy. And these are the explosions of red supergiant stars, and they have hydrogen in their spectrum, as I said. And recent notable examples, are 2023 IXF and 2024 GGI. 2023 IXF, we actually observed from the roof of the building at Queen's. And so that was a really fun experience. To actually see a supernova through the eyepiece of a telescope was a real great experience for me. And there is another layer of complexity with stripped envelope supernovae. These are still core collapse, but they're even more diverse, and I find that quite exciting. They're produced from massive stars which have lost their outer envelopes through either some strong stellar winds that are blowing material away from the surface of the star, or from interaction with a stellar companion where mass is transferred between the two stars, which can lead to a diverse range of outcomes. This graphic is showing that there's an inflated star and mass is flowing to this smaller, more yellow star. But this is quite a chaotic system. It's not particularly well understood, and the physics isn't well understood, how the material flows exactly, how it's accreted onto the other star. So this has an impact in the diversity of the explosions that we observe, which makes this quite an exciting thing to be working in, and is my own specific field of research. So how do we know that massive stars have exploded as supernovae? Well, we see the star and we see a point, a new supernova at that location. But really, the best piece of evidence, and what I think is really, really exceptional, is this set of 3 Hubble observations of a patch of sky. On the left, this image taken in 1997, I've labeled some stars, and the scale here has been marked about half arc second, and there are four stars and the green blob, as the brighter star. Now the white circle marks the location of the supernova. So in 2005, there's a supernova explosion, is really bright source at that location. And then when Hubble observed this patch of sky again in 2007, the star that was there in 1997 has now disappeared. So we actually know for certain that that star that was there before has exploded and disappeared, and that formed the supernova, which is this is incredible, and these results were published in Nature in 2009. So here I've taken 8 new images of supernovae discovered recently by our surveys, and I want to talk briefly about how do we find these supernova explosions. We use telescopes like ATLAS. ATLAS is the Asteroid Terrestrial Impact Last Alert System, and it's designed to do exactly what you might think. It's designed to find near-Earth objects that may be on a short-term collision course with Earth. And it observes a patch of sky 4 times per night. And it can, and the combined 4 telescope system, 2 in Hawaii, 1 here in Chile, and 1 in South Africa, can survey the whole night sky on a daily basis, taking 4 exposures per pointing. So the asteroid astronomers can look for objects that move between each observation, an asteroid, and they can calculate an orbit. But also, we use this data to discover supernovae. Because if you're surveying the whole night sky at a high cadence to a reasonable depth, we achieve about 19.5 magnitude in the 30-second exposure. We can find an awful lot of supernovae. And that's exactly what we do with ATLAS. So here are the discovery totals. ATLAS has discovered 1,000 near-Earth objects, 100 may be potentially hazardous, 100 comets, but 21,500 supernovae have been discovered with these telescopes. So I think it's an incredible supernova discovery machine, and we're very thankful to have the rights to use the data and use it to fuel our science. The animation I'm showing here is a representation of the pointings of the telescope over a couple months. And the telescopes work on a schedule, so each color here represents a different telescope, and each kind of flash represents a different night of observations. So it's observing all the time, almost every single night. And indeed, because we have four units in 3 geographical locations, 1 telescope is almost always in nighttime. So we're always scanning the sky in real time and processing this data to find supernovae. We also use the Pan-STARRS telescopes, which are a larger telescope than the half-meter ATLAS telescopes. These are 2-meter class telescopes, and there's 2 of them. And they have a high resolution, and because of the larger main mirror, a deeper image. And this data is used in the Supernova Hunters citizen science project. So you will, if you follow the link or search, just even Googling Supernova Hunters universe, you can review real Pan-STARRS observations and search for supernovae in that data, which is really cool. And it's something that we at the Queen's team and many other places spend a lot of time doing, is reviewing these images and finding new supernovae. But there's also a way for the public to get involved there as well, and it's strongly encouraged. It's a really great project that does yield really good results. But I want to talk a little bit more about one of my favorite techniques that we use, and it's called difference imaging. But first, I want to introduce this concept of a reference sky. If you're taking lots and lots of observations over many days, you can combine these images in the deep stack, achieving a depth much greater than a single exposure. And then we use this as a reference sky of it for any arbitrary sky position. And we term it a wallpaper because it's static, it's unchanging. It's the background upon which we search for new supernovae. But it's the similar technique and method to taking lots of observations of any source. If you do an astrophotography and then you stack the images to reduce the signal to noise and achieve a greater depth. Similar technique, just with the Atlas telescopes. So with this reference sky, this wallpaper, we're able to play this game that I like to call Spot the Difference with the Universe, where having our reference sky, we take any new observation and then we just subtract them. It's slightly more complicated than that, but the essence is we use a computer algorithm to subtract new observations, to subtract the wallpaper from new observations. And occasionally, like this image on the right here, we're left with a bright, shining new source, which is in this case, a supernova explosion, but could be in principle any number of transient or changing phenomena in the night sky, comets, asteroids, active galactic nuclei, things like that. But we use it for supernova science and supernova discovery. So it's a big computing project, really. At its heart, it is astronomy and discovery, but really the nuts and bolts of this project is computation. The data is streamed from Hawaii. We also take data from our colleagues and partners at this Wiki Transient facility that's processed through a broker called LASER. The Atlas units are marked here in Chile and South Africa, and there's a trial going on in Tenerife, but all of this data is piped to Queen's University Belfast, where we do the processing in real time in this big computing project. It's a large database, lots of images flowing in all the time. And a team of astronomers, myself and others, we review this data in real time, making discoveries as shortly as an hour after the telescope has observed that location of the sky. So we're really trying to make these discoveries in real time. And this is time domain astronomy is the field. And we're trying to do these things in real time. And with this information, then we can trigger other observations. We can contact observers at telescopes like the NTT, like I will be observing that tomorrow night, to urgently observe a new supernova. These things are not uncommon, but it's a race against time to be the first to find these supernovae, and that keeps things exciting and interesting, certainly. And I just want to highlight that there's incredible international competition in this field. Atlas and Pan-STARRS are the surveys that we operate with. ZTF is observing in California. Assassin is a network of small telescopes that are global. GOTO has a facility in La Palma. Gaia is the remarkable European Space Agency satellite, accurately mapping the locations of stars in the Milky Way, but it's also really good at finding new supernovae in external galaxies. On the bottom right is the Legacy Survey of Space and Time telescope. When this telescope is finally commissioned and operational, you'll be hearing a lot of it. It's going to revolutionize this field. It's going to be the most powerful discovery engine for supernovae that's ever been built. And we're really excited for that telescope to begin operating in Chile. And Black Gem is this 3-telescope system currently at the Lucia Observatory. And this is a photograph I took last year of one of the domes opening. There's a wealth of data and a wealth of observations, and they're happening all the time from all of these different telescopes, all these different sites. And the challenge in this field is trying to make sense of all these observations and combine the data together and try and understand something new. Here's a fun little graphic showing the field of view of these telescopes. So on the left-hand side is the Hyper Supreme Cam and Subaru, the Dark Energy Survey camera, and then the full moon for scale. And then there's the big players in this field, the ZTF camera, 47 square degrees. Pan-STARRS has a 7 square degree field of view, and the LSST, when it's finally commissioned and working, will have a 10 square degree field of view and survey the whole sky with an incredible camera, and produce really wonderful data for astronomers to use. So the process of supernova discovery goes like this. Once you have this point of light, you don't really know what it is. You've got this photometric discovery. You know that there's a bright source there, and you know how bright it is, but you don't really know, is it a supernova? Is it an asteroid? Is it an artifact? So the process is you make this discovery publicly. There's a server called the Transient Name Server. It's a public and anyone can access and take a look. It's just a website where people make this discovery claims of supernovae. And then teams like us at the NTT and surveys like PESTO check this website continually to try and find new candidate supernovae to observe. Then we take a spectrum in the way I described earlier, and we verified that this is a real supernova discovery, and we give it an SN designation. So before it's something called an AT, an astrophysical transient. For example, here I used AT 2024 QUB, but then once we get this spectrum and we get this proof that we know it's a supernova, we give it this SN designation, and we also make that claim publicly on the Transient Name Server. This game's all about getting public credit for the things that you do and the things you discover, and we use the Transient Name Server as a ledger by which to do that. And this game isn't really new. It's been going since the 2020s, and the term supernovae is only about as old as the 30s. But over time, on the x-axis here, we can see the number of supernovae discovered per year is increasing at a remarkable rate, because the y-axis here is in powers of 10. So we are close to 10,000 supernovae per year, which is a lot to keep track of, a lot of telescopes, a lot of observations. And it was only in 2017, here where I've marked the TNS, the Transient Name Server, that astronomers decided to get their act together and come up with some sort of centralized way to deal with all of these alerts. And with the number of new supernovae that are being discovered, the supernova zoo has expanded recently. The types and subtypes and narrow classifications, and it's a real taxonomy problem, and there's an incredible number of different subtypes. But we're revealing something new about stars, about how stars end their lives and how stars evolve. And we're able to study them in detail and understand not just one single event, but whole classes of event, where we're able to make statistically significant inferences and understand things at a population level rather than just an example of one. And it's an optimistic time to be in supernovae in this field of astronomy, because time domain transient astronomy is really in a golden age. And we expect exciting new telescope projects and instruments to broaden our understanding well through the 2020s and 2030s. But tonight, my task is to explain a little bit about the article that made the cover of Astronomy Ireland magazine, which I actually didn't know about until this meeting. So I'm very glad it made the cover. I'm very flattered, and I'm also very pleased to be able to talk about supernovae with you all tonight. This was a paper published in October on the Supernova 2022 JLI. It's a type 1c supernova, so it's one of those stripped envelope subtypes I was mentioning earlier. But the real interesting thing is that we found a periodic modulation in its light curve. But I would like to point out that this supernova, in this landscape of incredible professional sky surveys, observing all the time with machine-like precision, this supernova that I wrote a paper on that has been my focus and work for months, if not years at this point. A year and a half, was discovered by an amateur astronomer. This is an amateur astronomer contribution to supernova science, and without Berto Monard, who is here as LAG Monard, we wouldn't have had some crucial early observations of the source. So it's a remarkable amateur astronomer success story, and I was extremely pleased to be able to email and include Berto Monard as a co-author in this paper, because they certainly deserve it, and they were very excited about the interest in this discovery. I've included here a photograph of the host galaxy, an image of the host galaxy, NGC 157. It's a beautiful kind of face-on spiral galaxy. This image is from Chen et al. 2024. And in this, we take this look at the pre-explosion image of the region, where we don't see any kind of isolated stellar source, and then we see the after explosion panel B supernova. So unfortunately, we're not getting a progenitor detection here like we were for some other supernovae in the past, but it's still a very nearby, beautiful spiral galaxy, and we're able to get a lot of information about the explosion site of this supernova. But the headline is periodic modulation. That's something new for supernovae. This is a first of its kind discovery, and I'd like to talk a little bit about that now. Periodic modulation, though, in astronomy, in the universe, really tends to only mean one thing, is that there's some sort of orbit providing the interstellar clock, and that's what we observe in this supernova. So the orbit provides the clock, and I just like to play this video. I hope you can see it, which is the press release from our from our paper. So we find a link between the explosive deaths of massive stars and the formation of compact objects, these neutron stars, these black holes. And I'll just let the video play here and take a sip of water. Okay, so thank you all for watching that video. So I thought a picture is worth 1,000 words, and a video must be worth so many more. So I thought I would let that play, since we had such beautiful custom made graphics to try and explain the phenomena that we observed. So the general idea is that our supernova came from a binary, so a two-star system, and one of the stars underwent core collapse and formed the supernova explosion. But the system of two stars wasn't broken up by this explosion. The remnant from the supernova, the neutron star, stayed bound to this two-star system. And then what happens is, in this case, which is very, very rare for supernovae, is that the neutron star was on a grazing collision course with its companion star, meaning that every time the neutron star passed close to its companion, it's stealing some material and accreting that. And the process of accretion, of it essentially eating this material, is a luminous event, which causes an uptick in brightness. And that's the real observation that we made, is that there was, with a period of 12 and a half days, an increase in brightness from the supernova, where otherwise we wouldn't expect one. This plot is a plot taken from my paper. Apparent magnitude is just magnitudes. It's brightness, a logarithm of brightness, and then on the bottom here is MJD, and that's a modified Julian day unit that astronomers like to use, but it's essentially days. So each MJD is an Earth day. So using a range of telescopes, Atlas, ZTF, Assassin, the NTT, which I've mentioned before, Gaia, we were able to combine these observations and look across multiple bands, meaning that we're sampling in a different wavelength range of light. And I've plotted each of them separately here. But what I hope you can notice is that on the long decline from MJD 59,750 onwards, instead of being, as I might expect, a perfectly flat, smooth line, there's this bumpiness, this strange bumpy pattern to the supernova, and that's the periodic signal repeating like clockwork every 12 and a half days. And whenever you discover something like this for the first time, seeing something new in astronomy, you always want to interrogate your data. You want to figure out, is this my fault? So have I made a error in my code to make these plots or do this analysis? Is there some sort of systematic error at the telescopes, where there's some light that only turns on every 12 and a half days? Is there error in the instrument which we've used to make these measurements? But because in this case we observe this phenomena across multiple different telescopes, across multiple different observing sites, the telescopes in Hawaii saw the same thing that the telescopes in Chile and South Africa did. So we can, with a great deal of confidence, say that we believe this to be a signal of true astrophysical origin, and that's an important check to make and give us confidence moving forward. So here I've taken that kind of same plot on the left, but what I've done is I've plotted delta magnitude, which is essentially I've subtracted off the straight line that we saw before, and we're only looking at the signal from the wiggles. And then I've determined their period, and I've tried to make a dashed line plot of their behavior. And we see through these pretty muddled error bars that there is this one consistent signal of 12 and a half days throughout our entire data set, which is awesome. So we spoke to some of our theorist colleagues, and the model that we have in mind for this is something that goes a little bit like this plot on the right from Hirai and Podsilovsky paper in 2022. If you can see that a little white dot on this black square, that's a newly born neutron star in their simulation, and on the right is a stellar companion. So what we think, every 12 and a half days, something happens a little bit like this. If I can play my video, the neutron star comes in and grazes this star, disrupting it a little bit, but also making off with some matter. It comes in and steals it, makes off with it, and eats it. So that's the idea that we're working with, and the accepted understanding for what drives this incredible, unusual periodic modulation in the supernova. There's been some press about this, which I'm very glad to have been a part of. There was a PhysOrg article, Astronomy Ireland magazine. There was also an article in New Scientist, a strange supernova blasts hint we might have glimpsed a black hole's birth. We, in hindsight, think it's a neutron star, but the title was a black hole. But the only direct quote from me in that article was, "We've never seen anything quite like this," which I think is quite funny. And then there's also an article in French where they've stolen a picture of me from the QUB website. So, but it's very exciting to see plots that you've made and appear elsewhere without your knowledge. That's an interesting day whenever you refresh Twitter and you see you see the article come out. But for now, I would like actually to do a real example of supernova discovery. I would like right now to publicly discover a supernova while we're live, essentially. So this is live demonstration. So please do bear with me. Also, feel free at this point to say yes or no if you think it's a good supernova or not. This is the part of the talk where we can maybe have a little bit of audience participation, if that's okay. So here I am on our web pages, which we use as infrastructure to make these discoveries. This is the web page for Pan-STARRS, and it's the unfortunate job of a group of students to review almost 10,000 of these candidate supernovae. So this is a little insight into how some PhD students are having to spend their days. But whenever we load up the page, what we see is the right extension declination of any given source, its evolution and brightness over time. This is these magnitude MJD plots, so brightness over time plots. And then we also see on the right here the new image, the reference image, that wallpaper I described earlier, and then the difference where we see a bright new source. And also, I hope you can agree that it's not always as easy as the example I showed in the presentation. There are image artifacts and bands and imperfect subtractions to deal with. So it's really not a done deal. It still takes a bit of human interaction and human knowledge to really vet these candidates, which is where the Supernova Hunters Zooniverse project comes in. Perfect. So here's one I picked out earlier. I think this is a real supernova. Its magnitude is 19.3 magnitudes, and it's roughly equatorial. These are the coordinates, and it's in a galaxy NGC 5366. And I can just spend 10 seconds enjoying looking at the beautiful images of this galaxy. Here's a bright point. It's maybe a foreground star or something, but behind it we can see a spiral galaxy. We can see a bright point that isn't there in the reference image, and then whenever we do that computer differencing technique, we see a bright new source. So I think this is a supernova explosion, and I would like to make the discovery known to the world. Feel free to give a thumbs up in the Zoom chat or something. I don't know, but But I think it's real, and be reassuring to know if you thought so too. So here I've promoted this object to something we call the good list. And if I refresh the page, it's been given the IAU name 2024 KXC. So what we've just done is discover supernova, a candidate supernova, but that's, I think, still something quite remarkable. So I've just followed the link to the transient name server, which is a public website. And it's possible to search 2024 KXC and come back to the same page that I'm on right now. But here we have the discovery report, some of the information. So reporting group Pan-STARRS. So that's the telescope that we used. And here are some of the Pan-STARRS reporters, myself included. And we've publicly made this discovery right now. This is in UT time. But what we've done is we've told the world there's a supernova, a likely supernova here. Here, this is its location. This is its brightness. And we can wait for somebody to classify that, to go at it with a spectrograph, or maybe in the tomorrow night we might do it from here. So that's the process, which I think is really cool, and that can be Astronomy Ireland's supernova. And what I will do is I will go back and I'll leave a comment that we discovered it as part of the Astronomy Ireland June lecture, and I'll leave that as a public record, which will live there forever, which is cool. Here is another example, one I pulled out earlier. It's a 20th magnitude, so it's really quite faint. You need a 4-meter class telescope or larger to take a spectrum of this. But we will also promote this to the good list and make this discovery. It's the same process as I described before. Perfect. So that's Supernova 2024 KXD, which is, yeah, nice. It really never gets old making these kind of discoveries. I'll go back to the presentation, and I'd just like to thank you all for your attention. Yeah, I don't think one of the things you should do after traveling to high altitude is engage in public speaking. So thank you very much for your attention and patience. But yeah, just thank you very much for the opportunity to give a talk. And I'd like to finish with this little funny meme, and welcome any questions you might have.
Thank you very much indeed, Thomas. Our own supernova. What a thrill. Yeah, so if you have any questions, the usual format is you can pop them into the chat box. The chat numbers are popping up. Often they're compliments. We'll have a look at those in a second. Or if you want to turn on your microphone and just shout out something to Thomas, usually there aren't too many people competing for the microphone, so we can do it that way. Let's have, do you want to have a look at the chat box yourself, Thomas? Or
yes, yeah, I'm happy to. There's
by the way, while Thomas is having a quick look at the first one, I should say David Moore, Thomas Moore, were not related. It's just not it's not a piece of nepotism. He did all this on his own.
That's okay. We haven't looked too far back though, so maybe we should trace the family tree somewhat. So there's the first question here. Can I ask in your career how many you've classified? So for any given um, registered astrophysical transient candidate supernova, about 10 to 15% actually get classified. I would say in my career, I have registered somewhere in the region of 1,000 plus candidate supernovae, and I have classified actually about 100. So the ratio, excuse me, there is pretty good. So yeah, classified at the telescope myself about 100, and contributed to the discovery of about 1,000 candidates. Hope that answers your question. It's a good one, and certainly begs the question: why don't we get more telescope time and more observations? And yeah, I would direct those kinds of lines of inquiry to the time allocation committees at large observatories. We really do want more time. We want to do more of this science, and yeah, hope that answers your question.
Yeah, we can take a few more questions in the next 5 minutes or so, and then we want to tell everybody after the formalities of the talk about that big aurora coming this evening. So stay tuned.
Oh, yes,
But
absolutely.
if you want to take the next one, I see there's one there from Jose. What makes
Yes,
you
yeah,
decide that the compact object is a neutron star rather than a black hole?
yeah. So that's an interesting, that's a very good question, and something that we had to spend a bit of time to think about. But it comes back to the accretion rate to be as luminous as it is for us to be able to see these bumps. The compact object, neutron star or black hole, needs to gather matter fast enough to be luminous. There's a relationship between the amount of mass it's eating and how bright it is. And for it to be this bright, we know it needs to be a neutron star, because black holes, small stellar mass black holes like this, can't accrete, can't eat matter at the rate to power this luminosity. So that's why we think it needs to be a neutron star.
And I see Mike Egan and Sandra asks a similar question. How much do you see AI improving the discovery and
Well,
classification of
yes,
supernovae?
yeah, Mike, absolutely, yes. AI and um, machine learning is already proving to be crucial. Um, for every object that a human looks at in the pages I was showing before, about 100 are thrown away by machine learning. So that's cutting down on the human time needed to do this kind of work massively already. And the ZTF collaboration I mentioned earlier recently successfully discovered a new supernova, registered it publicly like we just did, pointed a telescope at it and observed it, and classified it, all without any human interaction. Now, it was a nearby supernova, it was reasonably bright, and it was a type 2 supernova, which makes up about 60% of the supernovae that we see in the night sky. Or it was a type 1A. It was one of the super common classes of supernovae that we see all the time. So the odds of it getting that right were pretty good. But still, we are taking steps towards AI improving the discovery and classification of supernovae and automating it, which when we go to larger surveys in the future, like the legacy survey of space and time, will be really crucial, because there just isn't enough human time really in our field to be making all of these kinds of decisions. We need some way to automate it, and we're making steps in that direction.
Yeah, if I might just abuse my position as the chair and come in with a quick question about the supernova in M101 last year that you were observing live from Queens. We also, I was looking at it too, and we were telling everyone, the weekly members, email to out and have a look. You don't get a chance that often. But wasn't that supernova varying up and down a lot as well? You remember?
Yes, it was um it did show some kinds of variation.
It faded
But
and then brightened again unexpectedly, and did that a couple of times, I think.
yes, yeah, it's a slightly different mechanism, but yes, it is also variable, and really it's our modern telescopes and observing strategies that allow us to catch these interesting episodes in the supernova's evolution. So yes, that did fade and re-brighten, um, uh, in a
But it
small
was
way,
the
but it
black
wasn't.
hole neutrons are compact
Yeah,
object reason.
no, it wasn't this
Yeah.
re-
Okay. I see.
repeating clockwork
I see. There's a
situation.
question there from Fergal Meath, which links into a bit of a question I was thinking of as well. He asks,
Mhm.
is your research tied to a particular set of telescopes? Can you get access to Webb? And I was also wondering, what happens to these telescopes with the full moon up? Do you have to stop observing? That's sort of three questions in one.
Yeah. So if the full moon's up, we still observe, but there's this kind of annulus around the moon that we just won't go into because we can't observe to a decent depth near the moon. But yes, we just use a different filter, which is less sensitive to scattered moonlight. But still, a full moon is a real problem for us, especially whenever the moon comes right in front of the bit of sky you want to observe. That's a problem. And yeah, the research we're doing is tied to a particular set of telescopes because those are the ones that we use to make the initial discovery. But then after that, we use a wide range of telescopes. Um, the Very Large Telescope, Swift. Recently, we have also used data from the Einstein Probe Telescope that's been recently launched. And indeed, we all want access to James Webb. But the time on that telescope is massively oversubscribed, and the pointing of the James Webb Space Telescope is such that it's quite difficult to observe any given target immediately because it doesn't want to point that wonderful big mirror in the direction of micrometeorites or even anywhere towards the sun. So access to Webb is 100% my goal, and I would love to have a proposal submitted and accepted to use James Webb.
Great. Let's see. Any other questions come in on the? Plenty of thanks. So that may have brought to the end of the formal questions, but obviously you're in Chile now, of course, but accessible through Queen's. I think if anybody wants to contact you, it's usually easy enough to find researchers through the Queen's University Belfast website. They probably
Yes,
have
yeah.
your email address then. Yeah.
Yes, yeah.
So
You're all welcome to
that
send an
was
email.
fantastic. That was fantastic, Thomas. Congratulations on the publication of the paper, even pre-PhD. I think supernova are fascinating. I've been lucky enough to see a few live in telescopes, and we always try to alert people you do need a good telescope to see them. Um, so hopefully those with telescopes did get a chance to see that one last year, and they'll get to see many more in the future. Now they know a lot more about what goes on in the research. And I wish you look in the future when these new giant telescopes come online, and there are millions of supernovae found every year.
Thank you very much, David. I appreciate that. Thank you.
Thank you very much. I'll talk about the aurora now. If you need to head off, Thomas, you've got plenty to do there in Chile, I'm sure. If not, welcome to stay and listen in.
Thank you. I'll stay and listen
All the
in,
best.
and thank you very much again for having me.
Our pleasure. Pop my video on there, not that you particularly need to see me for this, but I'm just going to briefly tell you about what to see in the sky, starting with that aurora this evening. It's supposed to be underway by now. Aurora are a bit tricky to forecast. Sometimes they can be early, 12 hours I've easily seen, and sometimes late. But doesn't seem to be any huge activity in what's called the auroral oval out there. But there's definitely been an enhancement during the day, but it isn't the big storm that we were expecting. Does that mean the explosion on the sun, June the 8th, 2 days ago, that was supposed to hit tonight, missed us, or it's delayed? We won't know till after the event. So I think all you can do is watch the night sky. It won't get dark this close to the solstice in Ireland till about 11 o'clock, maybe even later. Remember, midnight when the sky is darkest is technically 1:30 a.m. One, because we've put the clocks forward back at the end of March, and 30 a.m. because we're using Greenwich Mean Time. It's a half an hour around the Earth from Ireland. So 1:30 is really local midnight. So if you can stay up till 1:30, that's the darkest part of the night. Keep an eye on the north sky. If it's anything like May the 10th, you'll be seeing it overhead. Don't get your hopes up too high, but aurora are unpredictable. We may get nothing, we may get a storm, but it is a pretty strong one that they're forecasting for tonight, and they seemed pretty certain. I'm a bit disappointed it hasn't happened already. But good few of the alerts we put out on the social media do end up not materializing, or they happen when it's cloudy in Ireland, or there's a full moon in the sky. We don't have that tonight, but usually it's the Irish weather that ruins it. We were very lucky on May the 10th that NASA said best in 500 years happened when most of this island was clear. I think the big story is not the once in 500 years, it's the fact that Ireland had a clear sky. And you'll see the pages of the magazine are packed with pictures as a result. So that's the aurora. Just keep watching the sky. And if you see it, immediately email magazine@astronomy.ie just to tell us you saw it. You got a picture, great. But if it's just a report, that's even better. Give your location and we'll put it in the next issue of the magazine if we're reporting on a major June aurora along with a major May aurora. And we'd like to see more of these as the years tick by because we think the sunspot maximum will happen the end of this year, early next year, a bit earlier than originally expected. And aurora, believe it or not, the numbers tend to peak about 3 years after solar maximum. So it's early days yet. So keep watching that social media. We've been predicting these aurora for decades. We've had RTE, I remember a big news crew we had out in North County Dublin back in 2003. They got incredible footage for the 9 o'clock news that time. So stay tuned, is all we can say. What else happening in the sky? Well, on social media, see, there's been a whole bunch of these Starlink satellites launched. So there should be tight trains chasing each other across the sky. I've been thwarted by cloudy skies, but we're going to post those on our daily social media post. By the way, that daily social media post on Facebook, Instagram, Twitter happens before sunset. Remember, sunset's not till 10 p.m. this time of year. So we'll get it out there 8, 9 o'clock. That means we can leave it to the very last minute so we can give you the very latest information. And I'd always tell you what else is happening. For instance, the Beehive star cluster is near the moon tonight. I managed to see the moon last night. Tonight, so it was last night. No, it wasn't last night. It was the night before. And tonight it's going to be near the Beehive star cluster. If you get the magazines, a diagram showing what that will look like in your binoculars. Now, you won't need binoculars to see Saturn near the moon. That's not going to happen, though, until later in the month, on the 27th of June. But that is a really important event. It won't get very close. The moon won't get very close to Saturn, 6 degrees, so barely a binocular field of view apart. But the rings of Saturn are tilted almost edge on to us. And in fact, around that time, the end of June, the rings are tilted as close as they're going to get to edge on. It won't quite go edge on, about 2 degrees off. And then they'll start to open up again. I think it's about 10 degrees by November. And then they'll close down. And in March of next year, they will go exactly edge on and vanish, even in giant telescopes. So if you want to see Saturn the way it's supposed to be when it has no rings almost, any morning this month, especially that time when it's near the moon, June 27th, June 28th, they're the dates to set your alarm clock for. There's diagrams in the magazine, so watch out for that. The only other planet that's on view is in the morning skies as well is Mars. It's a bit to the left of Saturn and even harder to see. So not a great month for viewing planets. And it's not dark for very long at this time of year either, unfortunately. But the moon will get spectacularly close to the bright star Spica in Virgo. They're about a moon width or two apart when it gets dark on Sunday, June 16th. That's this coming Sunday. And if you can spot the moon in daylight, you can see them get within about a half of a moon width apart. So a small telescope will have Spica and the moon in the same field of view. I've seen that happen before. If you haven't got a small telescope, wait till it gets dark and see them about 1 or 2 moon widths apart on Sunday evening. That's all in the magazine as well. The summer solstice happens for the Northern Hemisphere at 9:50 p.m. on Thursday week. That's the official start of summer. It's not May the 1st. It's not June the 1st. Not any of these things that TV shows and other people try to tell you, even the Meteorological Service. They are all wrong. The The seasons are astronomical phenomena, but defined by the solstice and equinoxes. And the summer solstice on June the 20th this year marks the start of summer in the Northern Hemisphere. That means Ireland. Stick to that astronomical definition, no matter what they say. So that's everything that's happening. There's lots more in the magazines. Watch out for those Aurora, and the Starlink Times will be in the social media post in about an hour's time. In other events happening that aren't in the sky, our advanced classes start the end of this month. Beginners classes start October 22nd. All details are on the website, astronomy.ie. Big Starbecue is coming up August 31st. Lots of people have already booked for it. And our next lecture is on the second Monday of July, and that's July the 8th, and it's titled, Where Are the Sun's Sister Stars? So we know the sun was born in a gas cloud, and it was a member of a cluster of stars, and they all drifted apart. And Paul Fellows from the Cambridge Astronomical Association is going to tell us, can we track these down? A spoiler alert, yes, we can. And he's going to explain how it's done. And if that's too far ahead for you, tonight, 10 o'clock, BBC4, The Sky at Night by the BBC. Fantastic, longest running show in the history of television is on. Don't miss that. It'll be repeated, I think, on Thursday. That'll be warned about in our members' email on Wednesday. We warned you about tonight's episode last Wednesday. So do follow us for that. Twitter, Facebook, Instagram. We'll keep you posted there of anything new that comes up. If you're not a member of the club, please join. Order the magazine. You get that Aurora souvenir special. It's only going to be one in every 500 years, according to NASA. So well worth getting. So that's all the announcements. If I've forgotten anything else and any of the officers of the club are tuning in and want to put in, now's your chance. We'll give you a few seconds. Nope, I must have done everything. So enjoy. Let's hope that Aurora materializes tonight. If you can stay, it'll start to get bright again around 3 a.m. So if you're allowed to stay up till 3 a.m., I wouldn't give up till then, just in case. So thank you very much for everyone for joining us. A special thanks to Thomas Moore for a fantastic talk on supernova and a brilliant discovery I can be well proud of and bringing some of it to Irish shores. And we'll see you all again next month through the pages of Astronomy Ireland magazine. Have a good evening. Is that all okay? Laura, have you stopped the recording now? Oh, you have you?